Today we are going to discuss 6-membered ring system. Here one question for 6-membered ring system with 2 substituents. Here we take one example, 1,2-disubstituted cyclohexane, and in that 2 substituents are, first is acid and second one is also acid group. But here we take 2 structures, first one is cis and another one is trans. So first, suppose this is A reaction and this is B. At that time, first one acid molecule is present at the axial position and another at the equatorial position. When we can carry out first dissociation, at that time we get here first dissociation product, which is stable. Why this product is stable? First dissociation product of 1,2-dicarboxylic acid cyclohexane is stable. Why? Because of formation of hydrogen bonding. Due to hydrogen bond formation, there is a stable conformation. It gives a cyclic 6 or 7-membered ring system, and due to this formation of such a type of ring system, the structure is much stable, so that here we get a first dissociation product. After first dissociation product, second dissociation is carried out, but second dissociation is very much difficult. Second dissociation is much difficult than that of first dissociation. Why? Because first dissociation product is stable product, and so that it doesn't, or it is difficult to convert into the second dissociation product, and this is the second dissociation product. And another reason for a difficulty to form this product. Why? Because these 2 negative charges arises on this acid group, or due to loss of these 2 hydrogens from both of these acid groups. At that time it gives 2 negative charges, and we already known about that negative repulsion is carried out, and due to this negative repulsion, this molecule or this conformation is unstable. This conformation is unstable, so that here we doesn't get, or we get this product as a less stability. Okay, so the difference between first dissociation and second dissociation is greater. First dissociation and second dissociation, the difference in first and second dissociation is 2.72 units. This is the pKa value. Okay, this is somewhat large difference as compared to it is present in trans. Why? Because in trans isomer, first dissociation gives this product having a formation of acetate ion. In this acetate ion, we get here negative charge on this axial molecule. If we carry out this example, at that time both acid molecules are present at the axial position, and these axial positions are very sterically hindered. Means what? This acid group is sterically hindered, and also this one is sterically hindered. That's why there is no option for dissociation which will becomes first dissociate, so that out of these two anyone will get dissociated in first dissociation, so that we get here this product, either we get this one also. I write here the upper axial group, we can remove the hydrogen and dissociate, and it will gives this type of negative charge. But when we try to remove this hydrogen also, it give a negative charge on this acetate ion, and this is right. Okay, but here we get here this product. At that time this is also a somewhat sterically hindered, but less than that of first. Okay, so that this is not a stable, this is not stable, so that we write here unstable, because steric hindrance, and there is no formation of hydrogen bonding. There is no formation of hydrogen bonding. Why this is not formed? Yes, here this negative charge and hydrogen present on the another acid group, both are much away or far away from each other, and that's why they doesn't able to interact with each other, and so that there is no formation of hydrogen bond. Okay, that's why the structure or first dissociation product is somewhat unstable, and at that time unstable product can convert into another stable product, and or they will try to convert into the another stable product, so that this is unstable, and after second dissociation we get this product having both the acid group will convert into corresponding acetate ions. Okay, so that you see here these are the ions. Okay, these two ions are present, and you see here both of these groups are present at axial position, so that they are far away from each other. Negative repulsion is not formed. Negative repulsion is not formed. No repulsion between negative charges. Okay, so that this product is somewhat stable, and this product is somewhat stable. Okay, and from this explanation we can say that first dissociation and second dissociation product, difference between these two is less, and the difference is this is present in cis. Okay, and in trans we write here trans, its pK value is only 1.95. This is only 1.95. So I can give some explanation, or we can recap here. In first case, in cis isomer, at that time acid, both acid, one acid is present at axial and another one is at equatorial. Out of these two acid groups, one will dissociate, and out of these two, which is unstable, which is more bulkier, which will convert into the stable product, so that first axial proton will remove its hydrogen, acid group will remove its hydrogen and form a acetate ion at the axial position, which is unstable also, and at that time cis hydrogen present on the acid group is interact with the negative charge, and at that time it will form a hydrogen bonding, and due to formation of hydrogen bond, that product is somewhat stable. That's why it is unable to convert into the second dissociation, so that this is somewhat difficult than first one, and so that its difference is larger, 2.72. But in case of second trans conformation, we get here first dissociation product is somewhat unstable, it is unable to form hydrogen bonding, and in second dissociation it will doesn't able to convert into the second dissociation product. Why? Because there is no repulsion between negative charges. Why? Because they are far away from each other, and so that product is somewhat stable, so that both first and second dissociation product difference between that is only 1.95. It is only 1.95, so that we can give some explanation right like this. Okay, we are going to start. Next topic is merged substitution elimination reaction. Students, we take first example for this case. Suppose we are going to study about this molecule. Suppose this is NH2, and here we write this is OH. Okay, at that time, first we try to convert that planar structure into the chair conformation. Now here this is your chair, and here this NH2 group is represented by the dotted line, so that we can have some idea about what is the position in chair conformation, and its position is below the plane. Suppose this is your first carbon atom, and we write here this is NH2, and at the adjacent carbon atom we have hydroxyl group, and that hydroxyl group represented by the wedge line, and that wedge line means what? It is present at the beta position, so that we write here this OH at the beta position. Okay, and now when we can react that molecule with nitrous acid, HNO2, at that time that NH2 amino group will convert into the nitrogen. It will convert into the nitrogen, and here we write N2 plus. Okay, and this OH we write like this. Okay, this is your product, but that product is not stable. Why? Because the positive charge associated with this N2 molecule or N2, that's why this N2 will eliminate. So that we call this is elimination. This is elimination. Okay, so this N2 will eliminate. Okay, but this is not in a simple way. It requires some opposite push. Okay, so that this bond is opposite to this equatorial bond. Okay, this is one, and this one is second bond, which is exactly opposite to this eliminating group, so that it will give some pushing at back side. Okay, so that it will easily removed. Okay, now here we get its product. Ring contraction is there, and we have converted that 6 membered into the 5-membered ring system, and we try to draw that structure right like this. Okay, and this is your 5-membered ring system, and in 5-membered ring system that hydroxyl group is present like this. Here this is hydroxyl group, and here positive charges arises here, and the N2 nitrogen molecule, gas molecule, will liberate. Okay, here this nitrogen lived, and we get here 5-membered ring with positive charge, and at that time we can lose this H plus ion, and due to loss of this H plus ion we get here aldehyde group by stabilizing this positive charge, so that we get here aldehyde. Okay, so this is your final product, and we call this merged substitution reaction is also called as neighboring group participation. This is also an example of neighboring group participation. Okay, so in this case we learn about from the position of amino group and position of hydroxyl group. Suppose we take another example. Suppose this is an planar structure having amino and hydroxyl group, but its position is somewhat different. Okay, so suppose we write here this amino group is at alpha site, and this hydroxyl group is also present at alpha site. At that time we try to convert that into the chair conformation. In this chair conformation, this dotted line will give an idea about equatorial amino group. This is equatorial amino, and this hydroxyl group is also present at the alpha side, so that we write this by an axial position hydroxyl. Okay, now we react that with nitrous acid, and we get here product HNO2. We get next product HNO2, and HNO2 will react to convert that amino into the N2 plus, and this is your hydroxyl group OH, and at that time also we see here the eliminating group is N2, and anti to that eliminating group we have the ring bond. We have a ring bond, and this ring bond will attack at back side of the eliminating group, so that this is the neighboring group which is participated in this elimination reaction, so that we get here a next product which is also 5-membered ring system. Okay, suppose this is first carbon and this one is second carbon. At that time second carbon is now a part of the 6-membered ring system, but after participating that bond into the elimination of N2, at that time we get this second carbon atom is not a part of ring, and this is out of ring, so that we write here this is your final product, and final product is aldehyde. Final product is aldehyde. Now we take another example with different positions. Suppose this NH2 group is present or represented by wedge line, and hydroxyl group also represented by wedge line, NH2. Now here what we can change, wedge line means what? Beta position, so that we write that amino group at axial position. Okay, then after reacting with this with nitrous acid, we get here a different product. Why? Because this amino group is present at axial position. Now its product is here. After reacting with nitrous acid, we get here N2 plus, and N2 plus is somewhat unstable, so that it will require elimination. So now which group is used to eliminate this one? Okay, so how it will eliminate? At that time this hydrogen from this carbon atom is used to eliminate this N2 group. Why? Because this is anti to this nitrogen, and here minus of H plus is carried out, and this will go here, and N2 will remove, nitrogen gas will removed in this reaction, and we get here a next product having double bond, and here this is your OH. Now I write that hydroxyl group like this. This is not exactly at axial position and not exactly at the equatorial position. This is somewhat pseudoaxial or pseudo-equatorial position. Okay, so you remember why I write this one? Because this carbon atom is now sp2 hybridized. Now this carbon atom is sp2 hybridized, so that we can see here sp2 hybridization contain 120-degree angle, and that's why I doesn't write here not axial or not equatorial. It is somewhat pseudoaxial or pseudo-equatorial position due to presence of double bond. Okay, and in alkene system, this is one of the alkene system. In alkene system we can say that this is an enol. This is an example of enol, and in case of enol we get here tautomerization, and after tautomerization we get here product. What is the product? In this case tautomerization. Now this will go here, and this negate, it will abstract proton by removal of this double bond. Okay, now you get here, this is your product. Okay, so this is the cyclohexanone. Okay, cyclohexanone. Why? Because enol is converted into aldehyde or ketone, and that's why we get here this product. Okay, now we take another example like this. Here another example is, suppose this is 6-membered ring system, and having this is your NH2 at present at wedge line, and suppose we write this hydroxyl group by dotted line. At that time we write that planar conformation into the chair conformation, and here this is the position of amino group, and here axial position, alpha axial, is for hydroxyl group. Okay, and after addition of HNO2 we get here the product. This is N2 plus this is OH, and what is the final product for the removal of this N2 plus? How we write here a removal of this N2? Okay, now at that time this oxygen from the lone pair from oxygen will participate for the removal of this N2 group. At that time from alpha side it will interact with the N2 from back side or below the plane, at that time from above side this N2 will remove N2, and we write here its product like this. There are formation of 3-membered epoxide ring, and this is your product. Okay, so this is your alpha epoxide. Alpha epoxide is your product. Why? Because hydroxyl group is present at the below side, so that we get here alpha epoxide as a product. Okay.